Hey there, and welcome to This Explainer. Today, we're cutting right through all that industry hype and the endless buzzwords to look at the absolute foundational concepts of decentralized systems. I mean, you hear terms like blockchain, peer-to-peer, and distributed databases thrown around constantly, right? But what do they actually mean from a pure boots-on-the-ground engineering perspective? Well, we are going to break down exactly how these systems are fundamentally designed to be resilient, private, and scalable, mostly by doing one major thing: removing single points of failure.
To understand why any of this actually matters, I want you to ask yourself a pretty provocative question. What happens when the middleman fails? Seriously, imagine a system that relies entirely on one massive central server that basically holds everything together. If that single hub crashes or gets attacked or honestly just gets unplugged by accident, the entire network goes dark. Total blackout. That intense vulnerability, that's exactly what decentralized systems are built to completely avoid.
Let's visualize this. Think about a standard centralized model. All the individual nodes connect directly to one single hub. If that center fails, well, it's game over for everyone. But then, think about decentralized and distributed models. By adding a whole bunch of connections and multiple hubs, or even eliminating distinct hubs entirely, we create all these different paths for data to travel. In these types of architectures, if one station or link is completely destroyed, it's no big deal. The rest of the network just routes right around the damage and keeps on functioning. It is literally built for survival.
So here is our roadmap for today. We'll start with number 1, beyond the middleman. Then 2, a timeline of trust. 3, the hidden complexities. 4, the 3 axes. And finally, number 5, the DCS triangle compromise. Let's dive right in.
Section 1, Beyond the Middleman, Redefining the Network.
There is this fantastic quote from computer scientists Andrew Tannenbaum and Martin Van Steen that really hits the nail on the head. They define a distributed system as a collection of autonomous computing elements that appears to its users as a single coherent system. The real magic here is the illusion. You've got these entirely independent parts, nodes with their own unique hardware and software, but when you, the user, interact with it, it doesn't feel like some messy web of hundreds of computers. It just feels like one seamless, unified experience.
So how exactly do we pull off that illusion? Well, the answer is middleware. You can kind of think of middleware as the unsung hero of distributed systems. It's this software layer that sits right between local operating systems and applications, doing basically all the heavy lifting behind the scenes. It handles the communication to connect node A to node B seamlessly, and crucially, it provides what's called failure masking. That means if one computer crashes, the middleware completely hides that fact from you and just quietly reroutes to another one. All you ever see is one smooth, uninterrupted service.
Moving on to Section 2, a timeline of trust, from airplanes to Bitcoin.
You know, the need for fault tolerance definitely didn't start with cryptocurrency. It actually started with keeping airplanes in the sky. Back in the 1970s, systems like SIFT for aircraft control used multiple processors that would literally vote on results to prevent a catastrophic crash if just one computer failed. Fast forward a bit to the 2000s and we get peer-to-peer networks like Napster. Now this was an open network, but it had a massive fatal flaw: a centralized database for indexing. That became a single point of failure that eventually allowed it to be shut down completely. Then, in the 2010s, Bitcoin arrives on the scene. It took all these earlier concepts but added permissionless consensus. That means anyone could join or leave the network without ever having to ask a central authority for permission.
Now, to actually make these open systems work, engineers rely on a concept called state-machine replication. Basically, the goal is to make a group of totally independent servers act like one highly reliable machine. To pull this off, you absolutely need 2 things. Step 1 is agreement. Every single working node must receive every request. Nobody gets left in the dark. Step 2 is order. Every node has to process those requests in the exact same sequence. If everyone starts in the very same place, and they apply the exact same changes in the exact same order, well, they'll all arrive at the exact same final state.
And that brings us to the Bitcoin breakthrough. Bitcoin took these exact concepts to solve a huge issue in digital cash, which is the double spending problem. Think about it. How do you stop someone from just copying and spending the same digital dollar twice if there's no central bank to verify the transaction? Bitcoin solved this by using a distributed ledger. Instead of one single bank holding the one true book of accounts, every single participant in the network holds a copy of the permanent record, and they are constantly working together to agree on what's written inside it.
Which brings us to Section 3, the hidden complexities. When computers lie.
It's one thing to build a system where all the computers politely agree with each other.
But what on earth happens when a node just straight up lies? Or maybe it acts maliciously, sending confusing, contradictory information to the rest of the network. As you can imagine, removing the middleman introduces some truly massive engineering headaches.
Here are a few of the core challenges engineers are up against. First off, time. In a decentralized world, there is no master clock. Every individual computer's internal clock drifts slightly differently, making it incredibly hard to know which event actually happened first. Then you've got crash faults, where a node just abruptly dies. Even worse are Byzantine faults. This is where a node starts behaving erratically or maliciously to intentionally confuse the rest of the network. And finally, in open systems, you have to deal with Sybil attacks. Since identities are totally anonymous, one single person could potentially spin up thousands of fake identities to try and hijack majority control of the network. Engineers literally have to build massive, abstract mathematical models just to try and survive this messy reality.
But there is actually a completely different approach to these headaches, known as the Calm theorem. Calm stands for consistency as logical monotonicity. It basically asks, hey, when can we just skip all this expensive, complex coordination? And the answer is, when your system is monotonic. That means as the system gets new information, its conclusions only ever grow. They never have to be retracted. Actually, if you have that, nodes can work completely offline, completely independently, and when they finally sync up later on, there are zero messy conflicts to resolve. It's essentially the foundation of incredibly fast, local-first software.
All right, Section 4, the 3 axes, blowing up preconceived notions.
To truly wrap our heads around decentralization, we really need to look at Vitalik Buterin's brilliant framework. He argues that there isn't just one type of decentralization, there are actually 3 distinct axes. First up is the architectural axis. This is all about the hardware. How many physical computers actually make up the system? Second is the political axis. This one's about people and power. How many individuals or organizations actually control those computers? And third is the logical axis. This is all about the data itself. Does the system behave like one giant monolithic unit, or more like a disjointed, independent swarm?
Let's think about blockchains for a second. They are architecturally decentralized, right? They run on thousands of computers. They're also politically decentralized because they're controlled by thousands of different people. But they are logically centralized. The entire point of Bitcoin is that everyone must agree on one single global ledger. If you somehow split the network in half, it breaks. Now, contrast that with the English language. English is logically decentralized. There is no master server for English. If you cut the world's population in half, both halves would just keep speaking and evolving the language completely independently without needing a single global truth.
So this really begs the question, why do we actually want political decentralization? Why go through all the trouble to spread power out? Well, it's not just about making the network harder to break technically, it's about making it harder to corrupt socially. We want collusion resistance, meaning there are so many independent participants that it's virtually impossible for a small group to secretly coordinate a plan and cheat the rest of us. We want sovereignty, where you hold the keys to your own data and assets without asking permission from anyone. And we want egalitarian protocols. This means the rules ensure everyone has an equal opportunity to influence the system, rather than all the power just concentrating with the already wealthy or the early adopters. Let's head into our final part, Section 5. The DCS Triangle Compromise. You can't have it all.
Building these networks always comes down to trade-offs, and they are nicely mapped out in what's known as the DCS triangle. The 3 corners of this triangle represent our most desired properties. We have decentralization, spreading power across many participants. We have consistency, ensuring every single participant sees the exact same data at the exact same time. And we have scalability, ensuring the system can handle massive amounts of users and lightning-fast transactions effortlessly. But here is the harsh engineering reality, the ultimate compromise. A system can typically only achieve 2 of these 3 properties at the same time. No magic wand here. If you want a system that is incredibly scalable and perfectly consistent, it's very likely going to have to be centralized. If you want a massive decentralized network that guarantees perfect consistency, it's going to be slow and it's going to struggle to scale. You absolutely have to sacrifice one to maximize the other 2. Which leaves us with this final thought. Take a look at the apps you use every day, the money you spend, the huge amounts of data you generate. If you are the engineer building the network of tomorrow, knowing that you literally can't have it all, which side of the DCS triangle would you choose to sacrifice? Thank you so much for joining me for this explainer. Keep questioning the systems around you, and keep learning.